Alright, let's take a look at question number 51. In a coffee cup calorimeter, we have 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 hydrochloric acid. They are mixed to yield the following reaction: Ag aqueous plus chlorine ion aqueous, yielding a silver chloride precipitate. The solution, we're initially at 22.6 degrees Celsius and a final temperature of 23.40. Calculate the heat that accompanies this reaction in kilojoules per mole of AgCl form. Assume that the combined solution has a mass of 100 grams and specific heat capacity of 4.18 joules per gram Celsius. Okay, so basically what we have here, and this is what I like to do, is always draw a picture of what we have going on. So in our coffee cup calorimeter, we have two things that get put together. We get 50 mLs of the 0.1 molar AgNO3, and then we have 50 mLs of the 0.1 molar, and that should be big M, HCl. Okay, so we are basically doing a precipitate reaction. Okay, so what we first want to do is this. This is going to be kind of two steps. We're going to use the coffee cup to absorb the energy released, okay, when we are producing this product. All right, so we're going to determine the Q that is released during this. So there's our mass, specific heat, delta T. So let's go to work on doing that. All right. So our mass is a combined mass of 100 grams, which makes sense because we have 50 milliliters of water in each one of these solutions, so we're totaling 100 milliliters. So 100 grams times our specific heat, 4.18 joules per gram degree Celsius. And then our delta T is going to be our final temperature, which ends up being 23.40 degrees Celsius. And we subtract the initial temperature of 22.60 degrees Celsius. And that gives us a temperature change, a really small temperature change. So if we did this in lab, you really have to be careful to measure it carefully, of 0.8 degrees Celsius. So 0.8 degrees Celsius. Okay? We divide out our units, and this gives us a Q value of 334 joules. Okay, now this is not where we stop. This is just the Q, or the heat, that is being pulled out of this chemical reaction. It's exothermic because we end up at a higher temperature than what we started with. All right. But this is not for a full mole of reactants. Okay, we didn't start off with a full mole of reactants. We started off with less than a full mole. We have 0.1 molar, and we have 50 milliliters, so not even really close to a mole of substance. So we have to do a little work to get it into kilojoules per mole. The first thing is let's get this into kilojoules. So divide this by 1,000, and we get 33.4 kilojoules. Okay, so now we're halfway home. All right, now I just need to know how many moles I have of our reactants to be able to complete our story here. Now, here's the interesting thing. The kind of the nice thing is this, is because this is a 1-to-1-to-1 reaction, stoichiometrically, however much I have of one of these two, and I have the same amount, that's going to be my moles of product produced. So, but remember, 0.1, big M, stands for moles per 1 liter. Okay, and this is in milliliters. So once again, we're just going to have to change this into liters. All right, so we're going to multiply this by 0.050. Okay, so we took the 50 and divide it by 1,000. That gives us the 0.050 liters. Okay, to get the number of moles of products that I'm going to have at the end here. Okay, so when I do that, I end up getting 0.005 moles, and that's going to be of AgCl, or it would be Ag, or it would be Cl. Okay, we can do this because it's a 1:1:1 ratio. If it was different, we would have to do a stoichiometric conversion between what we were given and what we end up with. Okay, in this case, it's a fairly simple one. So here's my number of moles. Okay, I'm going to put that in here, 0.005 moles. All right, and when I end up calculating this, then I can get my delta H for this reaction. And the delta H is equal to 66.8 kilojoules per mole. Okay, and that was just dividing the 33.4 by the 0.005. Okay, last thing I want to do is I want to put my symbol on here. Now when we calculated Q, Q was for the energy that the water absorbed, which means that that water was raising in temperature. So if I want to put this 66 in my equation, it's going to go there as a plus on this. So this is going to be coming out of the bonds and into the water as far as energy. When it does that, and we talk in terms of the reaction is losing this energy. Okay, it was energy that was stored in bonds, and now it's energy that's been released to the surroundings or the water. All right, so that's where we have the negative, because this is energy that's going away. And we typically see that in exothermic reactions, because exothermic meaning energy is leaving, so it's going into the water surrounding the reaction, okay, and it's leaving the bonds. Okay, so that's how to do number 51.